Looking at number 8, we have to find any points of discontinuity for each of the following functions. So again, think about a discontinuity. A function has a discontinuity if one of the 3 requirements fails. What's the first requirement? When the function does not exist. So let's look at this function right here. When would this function not exist? When the input causes the denominator to be equal to 0. So what values of x are going to cause that denominator to be equal to 0? Well, we got to factor it. 2 numbers which multiply to 36 and add to negative 13. We know that when we factor a binomial, a trinomial, or quadratic for that matter, we're looking for a pair of binomials. X is going to lead us off. Negative 9 and negative 4 are our 2 numbers. What values of x cause each of these to be equal to 0? Well, 4 causes that one to be equal to 0, and 9 causes that one to be equal to 0. So we have discontinuities at x equals 4 and x equals 9. Now some of you eagle-eyed viewers are saying, well, wait a minute, we can cross out the x minus 4's. And that is true. However, crossing out the x minus 4's is actually changing the function. That's not the original function. This box is the original function. And in this original function, if x is 4 or 9, we get 0 in the denominator. Let's skip b and d for a second. Let's go to c. C, we have f of x is equal to the product of e to the x and sine x. Well, e is always continuous. We can graph that, no problem. Pen stays on the paper. You know what else is continuous? Sine. We can graph that. Actually, we can start back here. All right. These 2 functions are continuous for all real numbers. So if they're continuous for all real numbers, so is their product. No discontinuities. B and D are a lot like problem number 7. We have to check out what happens when we change. Now the condition for change in B is when x is equal to 1. Prior to 1 we do one thing, after 1 we do the other. So we have to plug 1 into both of these. Natural log of 1, that's something we should know, that's 0. Square root of 1 minus 1, pretty sure that's 0. Limit from the left and the limit from the right are the same. So this has no discontinuities. However, with D, we plug in 2, 1 minus 2. We plug in 2 for this one, 4 minus 4. One time we get negative 1, the other time we get 0. So we have a discontinuity at x equals 2. It's going to be this type of situation again. One function leaves off, the other one picks up, but not at the same values. And last but not least, with number 9, given the graph of f, why is f discontinuous at x equals 2? Well, the limit exists, right? My pens are going in the right direction, like they're going to meet. The function exists, oops, sorry about that, because we have a dot there, but there's not the same value. So the limit as x approaches 2 of our function does not equal f of 2. For part B, why is f continuous at x equals 3? Well, the limit exists, right? From both ends, we're heading to the same spot. The function exists, there's a point right there, and the value of the limit is equal to the value of the function. All right, so f of 3 exists. The limit as x approaches 3 of the function exists. And f of 3 equals the limit as x approaches 3 of f of x. Part C, why is f discontinuous at x equals 4? Well, we have ourselves a jump. We're down here, and we jump up. When we get that jump, we're looking at a limit issue. All right? The limit as we approach from the left is 2. The limit as we approach from the right is 4. Not the same values. So the limit as x approaches 4 of our function does not exist.